Hey, it's Mr. Allred, and we're continuing our discussion on functions, and we're going to pick up where we left off in the previous video with the graph of example 4 here. We were getting ready to state the domain. So, remember the domain is the x values. And this is kind of a funny graph, and it may be hard to tell exactly what's happening, so we might make some assumptions here, we might not. But it looks like we have some breaks in this graph. So it looks like our domain, it's kind of hard to tell, might run from -2 up to -1, and there's a hole there. And there's a hole there on both parts. So sometimes a graph doesn't necessarily have to be nice and smooth. And then it continues from -1 over to 4. And then it picks back up after 4 and goes to infinity. So just from the way this graph looks, there is a place here at 4 where if we drop a vertical line we hit nothing. And there's a place at -1 where we hit nothing. So there's no values when you plug in -1 or 4. And I'm assuming right now that this goes straight down at -2. We could argue about that possibly, but I'm not sure if we need to. Taking it from the looks of a graph is a little difficult sometimes. The range. Okay, so the range is the y values. So starting from the bottom, it looks like it's coming all the way up to -1. Now I know we have this flat line here, but it's kind of captured anyway. So it's going from -infinity up to -1, and then it picks back up here at 2, and looks like it's going to go on forever. So that is going to pick back up at 2 and go up forever is what it looks like. So a little bit different graph, but it gives you an idea of the x values that are being used and the y values that are being used. Okay, so let's talk a little bit about function notation. This will be pretty important. But graphing to this point has consisted of a set of xy points. Okay, so in that case we usually think of xy and calculating some points when we want to graph. So if you take the equation I've got here, y equals 2x plus 3, and if we want to think of it as a function, well, if you have background there, this is a y equals mx plus b, so it's a straight line. So it is a function because it'd be a straight line going across, so it would pass the vertical line test. But to denote it as a function, which is more powerful than just an equation, we use, instead of y, we use f of x. Now, f of x is considered the same thing as y as far as an output and how we would plot it, but it carries that little extra meaning to it, that it follows that function definition. So that f, parentheses, x in parentheses, is read as f of x. So f is the name of the function, as I have here. Okay, so if we have more than one equation, it's helpful to kind of give it a name, like f, g, or h, but if we had an area function, we might call it a of x, or a of s for side. X is the input variable, so that's representing the domain, and f of x we just said would be counted kind of as y, but that would be the output. Okay, so you'll see some more examples of how this is used in a moment. So it's a little tricky to get used to it until you get to use it as much as you possibly can. So let's do some examples. So from that first thing we just saw, we could have the function which is f of x equals 2x plus 3. So that's basically our input-output definition. That's our rule. That's our assignment. Okay. And then we want to talk about f of 2. So now I'm picking an input. I'm picking a very specific input. So that's an x value. And what I'm going to do is I'm going to take it and I'm going to plug it everywhere 2 is on the other side. Excuse me, everywhere x is on the other side. Let me erase this. It got a little out of hand. So let's see here. 2 times something plus 3, and the something I'm going to put in there is 2. So I'm replacing that x with 2. So it's an input position. It's a placeholder, and I plug it in. Basically, I get the same thing as f of 2 equals 7. So this pretty much corresponds to the point where x is 2, y is 7. But with the notation, we can refer back to the equation. And we can also be very specific to the point we're talking about and denote that it's a function at the same time, but it follows all the definitions set by being a function. So here's a couple of functions we're going to just evaluate, give us a chance to work on these. So the first one here, f of x equals 4x minus 7, and we want to find f of 2. So that would be 4, the x is a placeholder, minus 7. So 4 times 2 minus 7. So just to kind of give you the idea here, that 2 is going in everywhere there's an x. And then we would evaluate it, and we'd have f of 2 equals 8 minus 7, which would be 1. So you can almost think about that as a point where x is 2, y is 1. The second one here, function g of x equals 2x squared minus 3x plus 4. So if we want to find g of 3, we'll say 2 times 3 squared minus 3 times 3 plus 4. And once again, we're plugging that 3 in every placeholder, every x. And we're doing the function there. So g of 3 equals 2 times 9 would be 18 minus 9 plus 4. So a little bit more evaluation. G of 3 would be, looks like 13. So there's a place where x would be 3, y would be 13. The last one over here, h of x equals 4x all over x minus 3. So if I want to find h of 4, that would be 4 times 4 over 4 minus 3. So once again, everywhere I have an x, I'm replacing it with my input here of 4. So I can plug anything in I want, but this tells me what I'm supposed to plug in. So h of 4 equals 16 over 1, which is just 16. Alright, let's see here. I think it's a good time to end this video for the next one.